All right. Okay. So let's talk a little bit. Okay, last time we talked about the sleeper and the bending of the sleeper and the bearing stresses between the sleeper and the ballast. So now we're going to continue going down. So the analysis that we gave last week looked at the stresses between the bottom of the sleeper and the top of the ballast. Now we want to talk about the distribution of stresses through the ballast and into the subgrade, through the ballast, subgrade, ballast, and subgrade. Now, there are a couple of different models that I'm going to show you. Two of them in particular I'm going to spend a little time on. One of them is a very simplistic approach called the load spread approach, and the other one is a empirical model that is very commonly used. And then I'll show you, just very briefly touch upon some of the more sophisticated models. This is an area where you can get very, very sophisticated very, very quickly. I just want to at least familiarize you with some of those. Okay. So as I said, the most simplistic approach is the load spread approach. And that basically says that the tie, the pressure underneath the bottom of the tie, which is usually called, which we usually refer to as P sub A, is distributed as a function of the cross-sectional area of the of the zone underneath the sleeper, where the angle of spread is between 1.1 and 1.2, 1 and 1 and 1 and 2. So what it basically says is, so if in this particular case I have a 1 and 2 spread, it says that if I go down a half a meter here, so if this is a half a meter, then my area on the bottom this cross-sectional area with a 1 and 2 spread becomes the base, the sleeper length plus 1, and it's 1 because I have 0.05. Because if I'm going down 1 and 2, I'm going down. Sorry, if I go down 2, I'm going down. So it's plus 0.25 on this side and 0.25 on this side. So the base becomes, so the length becomes B plus 0.5. And the width likewise has that same spread because I have the same spread across the widths. So the width becomes width plus 0.5. And if I go down any length of Z, depending on what my angle of my spread is, I calculate my area. So let's do let's look at it from a more consistent point of view. I have my sleeper. I have my 2 sleeper loads. F and F. Now you all remember the sleeper loads, right? The sleeper loads are nothing more than what we did before. Let's go back here and just refresh you what the sleeper loads are. Each sleeper load was K W of X times A. So we know the deflection, we know the stiffness, we know the sleeper spacing. We can then calculate the sleeper load at any point X. So if you recall this particular example, this was with a 90-ton wagon. The sleeper directly under the wheel was about 34 kilonewtons, 34.8 kilonewtons. The next sleeper over was about 30 kilonewtons. The next sleeper over was about 20.6 kilonewtons, et cetera, et cetera. So that's what our F is. And we have two of them because with the sleeper, we have one on each rail. That F was for a wheel load. And so now, if we look at a 1.1 spread, just to make life easier, so this slope now is 1-to-1. So this length, so if for a depth Z, this and the sleeper length again is B. So this is B plus Z on this side and plus Z on that side. So it becomes B plus 2Z is the length. Sorry. B is the width in this particular case. Sorry, B is the width and L is the length. So this is, I drew this wrong. This is L. L plus 2Z is the length, B is the width, and this is the instantaneous cross-sectional area. Any place at any depth Z with a 1-to-1 spread, and the stress is equal to 2 F sub T divided by that cross-sectional area. Now, if we also remember that we can also do it in terms of P sub A, where P sub A is the pressure at the bottom of the sleeper at the top of the ballast. So if we know P sub A, and remember P sub A, we did back. P sub A is equal to 2F over 2/3 the base times the width times the length of the sleeper. Why 2/3? Because of this type of effect. So P sub A is the pressure directly under the sleeper, which is equal to 2F over 2/3 B times L. P sub C is the pressure at any depth Z. B is the width of the sleeper, L is the length of the sleeper. So if we did an example, if we calculated our dynamic wheel load to be 222 kilonewtons, and we say our center sleeper carries 25% of the load, the sleeper load would be 55.6 K sub N. Remember, this is K W sub X sub A times A, where A is the sleeper spacing, K is the stiffness, and W is the deflection. So if my sleeper is 0.23 meters wide and 2.59 meters long, at a depth Z, and if I assume a 1-to-1 source, so if I assume a depth of a 0.5 meter, so if we come back and we look at this equation right over here, the pressure at a 0.5 meter is 2 times 55.6, which is 2F, divided by 0.23 plus 0.5 to plus 0.5, so that's 1.23. And then the L is 2.59 plus 0.5 plus 0.5. So again, if Z, let's use the other mark, the pen, so it's a little bit easier. So if Z is a 0.5 meter, then my length here is L plus 0.5 plus 0.5, or 1 plus L. So if my length is 2.59 meters, my combined length, the length, if the sleeper length is 2.5 meters, at a half a meter down is 3.59. It's 3.59 meters long, 1.23 meters wide, and I can calculate my pressure, therefore, as 2F divided by the area at that point, which comes out to be about 25 kilopascals.
Excuse me, what is 1.23?
1.23. Okay, so we have the sleeper length and we have the sleeper width, right? So the same one-to-one slope we see in the width as well as the length. So the 1.23 is the 0.23 width of the sleeper, which is this, plus a half a meter here, plus a half a meter here. So it's 0.23 plus 0.5 plus 0.5, or 1.23. So we have this growth of we have this widening effect, not only in the length, but also in the width direction, because it's two-dimensional. Everybody clear on this?
No, can you expand again?
Okay. All right, so let's come back here. I have a sleeper, right? The length of the sleeper is L, the width of the sleeper is small b, okay? So the cross-sectional area under the sleeper is L times b. If I want to look at the area, the equivalent cross-sectional area at a depth Z, and for the moment, let's make life easier and let's make this a 1-to-1 slope rather than a 1-to-2 slope, just because the math is a little bit easier. So at a depth Z, this length over here is L plus Z, which is that, plus Z, which is that, or L plus 2Z. So if my Z is a half a meter, if I'm a half a meter down, and my sleeper length is 2.59 meters, it's 2.59 meters plus 0.5 meters plus 0.5 meters, or 3.59 meters. That's my length at depth Z. I have the same thing happening with my width. If I look at the side of my sleeper, which is B, I have the same thing happening. And again, let's assume a 1-to-1 slope. So at a depth Z, I have B, Z, and Z. So my total length here is B plus 2Z. So if my width is 0.23 meters and my depth is a half a meter, then the width at down at a half-meter depth is 1.23. So I know at this point in time, where am I? So I know that at this depth Z, my equivalent cross-sectional area is B plus 2Z times L plus 2Z. So my stress, P sub C, is 2F, where F is the sleeper load at the rail seat, divided by that area. Is it clear? All you're doing is taking a cross-sectional area. As you go down through here, the cross-sectional area increases because you have this shear effect on going through your ballast. As you go deeper into ballast, the area that you're spreading your load over increases. Are we clear? Is that clear now?
Yes, thank you.
Okay. So that's one way of calculating it. A second way of calculating it, in fact, the one I'm probably going to have you do most of the time in this class. When I give you a problem in this class, I'll tell you which approach I want you to take. But there is an empirical equation called the Talbot equation that was developed with about 40 years worth of testing. And there's about a nice 1,200-page book full of nothing but test data called the Talbot reports. And it just goes through tons and tons and tons of test data. And what it ended up coming up with, it ended up using the test data, it ended up developing an empirical equation for the stress at any given depth Z. So the stress at depth Z is P sub A divided by 5.9 times Z to the 1.25 in metric units, where Z is the depth in meters, the ballast pressure is in kilopascals, and P sub A, of course, is the pressure underneath the sleeper. So what this tells you is that this actually gives you the ability to look at the reduction in pressure as you go deeper into the ballast. So if you look at if P sub C is so P sub C at 0.3 meters, the pressure at 0.3 meters is about 76% of the pressure directly under the sleeper. At 0.4 meters, it's about 53%. At 0.5 meters, it's about 40%. And at 0.6 meters is about 32%. So you can see how the pressure decreases as you go down below the bottom of the sleeper.
And I have a question.
Yeah.
This empiric formula, it's for ballast 1-to-1 or 1-to-2?
It's for any ballast layer. The 1-to-1 is an assumption you have to make. And it depends on the shear properties of the ballast. This equation was developed for generally good ballast. So this is usually good for a good ballast layer, which probably has really a 1 to 1.5 type of ratio, but it's a good intermediate type of ballast condition.
Okay.
So let's do an example. Fact. All right, let's do this example. If the pressure of the bottom of the sleeper is 400 kilopascals. Now remember how you get the pressure at the bottom of the sleeper. Pressure at the bottom of the sleeper is 2F divided by 2/3 BL, right? So this is the width of the sleeper, this is the length of the sleeper. So the pressure at the bottom of the sleeper. So if the pressure at the bottom of the sleeper is 400 kilopascals, at what depth do you need to have allowable bearing stress of 100? If your allowable bearing stress is 172 kilopascals, if your subgrade only allows 172 kilopascals, which by the way is a fairly standard type of design value. Several of the manuals out there use between 150 and 170 kilopascals as the design stress for the top of the subgrade. And that's good for most subgrades other than the very, very weak subgrades. Like if you have a peat or you have a very expansive clay that becomes very soft when it gets moist, then it will be lower. So you can, so this is 172. This is 400. If you solve for Z, you get 0.475 meters. It's a fairly straightforward equation to apply. There's a problem that you'll be working on it there. Another way of doing the same problem is, again, if you just look, if you just want to use the ratio here. So if we took the same problem I just gave you before, if P sub A is equal to 400, and you're setting P sub C has to be less than 172 kilopascals, then if you use 40%, if you use a depth of 0.4 meters, you're about 0.53 times 400. So you're a little bit too high. You're a little bit over 200 here. If you use 0.5 meters, you're about 160. So you can see you just need a little bit less than 0.5 meters, about 0.49 meters of ballast. Now, when you're dealing with ballast, just remember you can't apply ballast to the nearest centimeter or so, because the ballast particles themselves tend to be about 10-12 millimeters each. So, or larger, depending on the depth of the ballast. So typically, if you round up to the nearest 0.1 meter, you're probably okay.
Question, please.
Yeah.
What is the difference between the ballast and the subgrade according to these formulas? Is it the same formula for each calculation?
Okay.
So you once wrote, you once wrote ballast and then you wrote subgrade. So
Okay.
is it the same meaning?
No.
No, of course it's not the same, but the formula.
The formula is the same. Yes.
Mm-hmm.
Because this formula is pressure, is the distribution of pressure through the ballast.
Okay.
And typically the way you usually do this formula. So let's have my sleeper here. I have my ballast layer here. I have my subballast layer here. Typically speaking, you use this formula when you want to figure out how deep a level of ballast I need in order to avoid overstressing my subgrade. So if I have a good, strong subgrade, it may have a bearing stress of 200 kilopascals. And so I can calculate my Z for P sub C equal to 200. If it was a very, very weak subgrade, it may have a bearing stress of 100 kilopascals. And then I have to solve my Z for P sub C equals 100. So typically the subgrade usually enters into this formula as the P sub C value, the pressure you want to get down to below so that you don't overstress the subgrade.
To the level of the subgrade. The pressure on the level of the subgrade.
Right.
Mhm.
And so what you're doing is you're really calculating a depth of ballast.
Mhm.
Basically, what we're saying here is if I have a very good subgrade, I can get away with much less ballast. Again, let's take this case here. If my subgrade can take 200 megapascal, 200 kilopascals, and my pressure on the bottom of my sleeper is 400, then I need about 0.4 meters of ballast. If my pressure is 100, if my allowable pressure for my subgrade is 100, then I need more than 0.6 meters of ballast. I probably need closer to about 0.65 or 0.7 meters of ballast. We can solve exactly in this formula. But you can see here, this would be about 120. So 0.6 meters of ballast is not enough if my subgrade can only take 100. And so, and I actually have the same issue now. I also have the same issue if I have a subballast layer. Basically, has Arkady gone through the difference between a ballast and subballast with you? Has that been discussed, the difference between the ballast layer and the subballast layer?
Not yet.
No.
Okay. You know, so sometimes I think I need to add a lecture in here just to give you an introduction to the track structure, because I find that a lot of times there's some concepts you don't quite get. I think in the future we'll have to add a lecture on introduction to this track structure. Okay. All right. So basically, underneath the sleeper, I have my ballast, which is usually a very, very high quality, high strength granular material, which is also tends to be very expensive. Like, for example, in the United States, we use a lot of granite. And granite is not found everywhere in the country. So it's not at all uncommon to ship granite 500 kilometers or 600 kilometers to be used on the railroad ballast. So it's very expensive. In fact, the shipping cost becomes greater than the cost of the ballast material itself. So you only want to put enough of a layer of ballast in there to cover very high stresses. You can then, between the ballast and the subballast, you can have between the ballast and the subgrade, because the subgrade is the soil. Between the ballast and the subgrade, you can have a second layer, which is a subballast layer, which is a less expensive, less high quality, but still strong granular material. So it's cheaper than the top ballast layer, but it's stronger than the sub-ballast. So, so let's say your ballast is good for 400 kilopascals. Your sub-ballast is good for 300 kilopascals. And your subgrade is good for 200 kilopascals. So you can calculate a depth of ballast, so you can get away with probably 0.3 meters of ballast, or maybe even less than that, maybe 0.25 meters of ballast, then maybe another 0.25 meters of sub-ballast, and then you'll have a granular layer of a half a meter, which will bring you down to 200 to the 200 kilopascal layer that you want. And so you can also use this equation here to calculate the depth of the ballast layer, as well as the combined depth of the ballast and sub-ballast layer. So you can use this equation to calculate your stresses at any point through the ballast layer. So it becomes a very, very useful equation for using to try to determine what depth of ballast, what depth of sub-ballast, what depth of granular material do I need to support my load. Everybody clear on this? You could, by the way, you can also use the pyramid of stress equation too, but it's not as convenient. This is a much cleaner equation. Now, I warn you that if you do the same problem using the pyramid of stress and using the pressure, the Talbot equation, you will not get the same answer. And the reason is exactly what the comment that was made before. When you do a pyramid of stress calculation, you have to assume a shear. You have to assume a slope of this layer here. And typically you will not get the same answer as the Talbot equation, because the Talbot equation is more geared to about a 1.5, a 1 to 1.5 slope. Any other questions on this? It's a pretty straightforward formula. Oh, one other problem. Like all empirical equations, it's only valid for the range that it's been calibrated for. So it's pretty good in the range of about 0.3 to about 0.7. Less than about 0.3 meters and greater than about 0.75, 0.8 meters, it really starts going outside its range of calibration, and it starts introducing some errors. But most ballast layers are generally in the range of about 0.3 to 0.6 meters. Very, very, very seldom do you have ballast layers that are greater than about 0.6 meters. Then you start using other techniques, which I actually won't get into in this class because that's supposed to be taught by Arkady in his lectures. So does everybody understand how you would use an equation like this? So again, if you know P sub A, you can calculate the stress at any length and any zone Z using either the load spreader formula, or I happen to like the Talbot equation because it's pretty simple to use and pretty effective in analysis. It can also be used to give you your ballast pressure at depth Z. So you can use it either to solve for the depth that you have a given ballast pressure for, or you can you calculate the ballast pressure as a function of the depth, either way. Now, as I said, both these models are fairly simplistic. And there are some other models that I just want to introduce you to. But we're not going to be really requiring you to use this in this class or in my exam, but I want you to be exposed to it. The next level up of sophistication is what's called the Love equation, which is used to calculate the distribution of load on a uniformly loaded circle. So this is similar to some of the highway type of situations where you use a loading plate in the shape of a circle to calculate bearing stresses. And so the Love equation says that the stress at ballast, the stress at length Z. So in this particular case, Z is equal to H in this equation. So the stress at depth Z is equal to P sub A, which is the pressure under the tie, same as in the Talbot equation, times 1 minus 1 over R squared over A squared to the 3/2, where R squared is the radius of the tie bearing plate that you use to calculate the equivalent ballast pressure. So in this particular equation, it's basically replacing a rectangular tie with a plate of equivalent area, calculating the radius of that plate, and then using this equation to calculate the bearing pressure. The problem with all of these equations up until now is that they assume a ballast property. So a more sophisticated type of a model would be something like the Boussinesq elastic theory, which would use the distribution of load through a semi-infinite homogeneous elastic half space. So this basically assumes the ballast layer is a semi-infinite elastic half space. You apply a load, again, the load again, P sub A is the load underneath the tie. And here we now enter into the shear behavior of the elastic half space. This shows you a comparison of the Boussinesq model as opposed to the load spread model. You can see the Boussinesq model gives you slightly higher stresses at lower depths, and then at greater depths, it gives you very similar to 2-to-1. Schramm model, and I'm just throwing these out because I want you to know they're out there. This uses the vertical pressure as a function of the angle of internal friction of the ballasts. So here we have a term theta, which we introduce, which is the angle of internal pressure of the ballast. And again, you can see there's some sort of variation between the various models. 5 is the Talbot equation. 4 is the Schramm equation. 1 is the Boussinesq equation. So this is a load spread. This is a Boussinesq. This is Talbot. You can see of these models, Talbot's actually the most conservative. Gives you the highest stress value. And then, of course, there are the multi-layer finite element models, of which there are dozens of these models out there. There have been some models that have been developed over the course of the last 30 or 40 years, which are actually quite good and now allow you to actually have a ballast, a subballast, and multiple subgrade layers. And but you need to have a very good knowledge of the properties of the ballast. For the purposes of this class, and for the purposes of most of your applications in the real world, I strongly recommend the Talbot equation. I find it to be a very, very effective model. I find it to be fairly easy to use and very commonly used in many parts of the world. Okay. I'm going to be leaving this distribution of load section now and going into rail. So before I leave the distribution of load section, let me open this up to questions. Does anybody have any questions about any of the things that we've done up until now? Going through the distribution of load, going through the beam and elastic foundation theory, going through rail bending stresses. We're going to come back to rail bending stresses again because I'm going to talk about rail in a few moments. Talk about tie bending stresses and ballast stresses. Anybody have any questions about any of this? Okay, again, as you go through the problems, as you go through the exercises, you have any questions, please don't hesitate to email me. I try to answer your emails as much as possible. Oh, one thing. I noticed in the last couple of batches, one email ended up going into my junk email. I have no idea why, but one email went into your junk email. If you don't get an answer back from me in a day or two, check back with me again, because I have to admit I don't check my junk email very often. And so it took me a couple of days to catch that one email and get back to the person. So if generally speaking, I try to get back within a couple of days. If I don't get back within a few days to you, try reaching out to me again to see if we can, if I missed your email or if I just didn't see it. Okay, now we're going to go into my favorite subject, which is going to be rail. You're going to get about almost 2 full classes of rail in here. And that's because Arkady and I agreed that I'm going to cover rail for this class in all its gory detail. Rail is a very, very, very interesting component of the track structure. When we look at derailment behavior and causes, rail is one of the top derailment causes out there. Rail tends to be one of the largest maintenance costs in here. We're also going to talk about surfacing and geometry in another course, but rail is one of the major elements in the track structure from a load point of view, from a failure point of view, from a maintenance point of view, and from a cost point of view. So we're going to spend a little bit of time talking about rail. Oh, what happened here? What just happened? All right. So the rail, and you've seen this picture now a lot because I like this picture, it makes a point. The rail is the element of the track structure that interacts directly with the wheel. So it is the area of by far the largest stress environment, the highest stress environment in the entire railroad world. Railroad rail is a very high quality steel. Railroad rail is significantly stronger than structural steel that you see using in buildings, for example. It's about, tends to be maybe 3 to 4 times as strong as standard building structural steel. It's also more expensive, not quite the same price and level as aircraft steel, but very high quality, very high strength steel. Rail is defined by its section size, which in the metric world is its weight in kilograms per meter. So UIC 60, which is for all practical purposes the largest of the UIC sections, UIC being International Union of Railroads or Union International Chemin de Fer. It is the they publish one set of rail standards. You'll see. Well, let's take a step back. Rail usually has a designation consisting of a letter and a number. So UIC 60 means that it's a UIC rail section. The section was developed, designed, and published by UIC, and it's 60 kilograms per meter. So the weight of this rail section is 60 kilograms per meter. A meter of rail weighs about 60 kilograms. A kilometer of rail weighs 60,000 kilograms or 60 tons. Was that right? No, did I miss something? No. 60 kilograms per meter. Yeah. So a kilometer would be, yes, would be about 60,000 kilograms or 60 tons. S54 refers to a British section design with a 54 kilogram per meter weight. S49 is a 49 per kilogram per meter weight. You can see the exact weights are a little bit different: 60.34, 54.59, 43.43. Now, take a look at the differences between rail sections. The heavier the rail section, the taller the rail section, the larger the head of the rail. Notice the UIC 60 rail section is wider than the other two sections. It's 72 millimeters wide as opposed to 67 millimeters wide. It's higher, it's 172 millimeters as opposed to about 150 millimeters. As a result, it will have a larger moment of inertia, which means it's stronger in bending. Also, because you buy rail by weight, the cost of rail is in euros per kilogram, or euros per ton, actually, or dollars per ton, depending on where you're buying it. And the heavier the rail section, the more expensive it is to put down a kilometer of rail. If you look at the design of a rail section, you'll see it's actually a fairly sophisticated design. You know, we obviously have the width of the railhead. We obviously have a height of the railhead. This particular drawing shows the moment of inertia around the x-axis there. the horizontal moment of inertia around the y-axis. But you notice, let's get rid of all this stuff over here. You notice there is a radius, there's a central radius on the railhead. There's a transition radius. There's a corner radius. There's a slight slope at the edge of the rail. This radius is designed to optimize the wheel rail contact stresses. And I'm going to be spending a lot of time talking about that in this class, because that's a very, very important element. And how do you control your stresses in your rail? And how do you control the degradation of the surface of the rail, as well as the internal degradation of the rail, development of defects? So this radius, for example, you can see in this UIC 60 section, the central radius here is about 300 millimeters. That's this radius over here. Then there's a transition radius of about 80 millimeters. And then there's a corner radius of about 13 millimeters. So you can see that there is there are distinct radius. It's this central radius that becomes very important. This top of the rail is referred to as the head. This bottom is referred to as the base. And the center portion is referred to as the web of the rail. And notice, of course, that you have fillet radius under the head. You have fillet radius to the base. By the way, these fillet radius designs are also very important, because as I'll show you when we talk about rail defects in a future class, a poorly designed transition radius, say, in the fillet of the railhead, can result in the development of defects right at that fillet radius and failure. There's another way of looking the different rail sections. I happen to be using North American rail sections, and before we get too far, you know, in the English world, or in the AAR world, the weight of the rail is in pounds per yard. So the UIC rails are in kilograms per meter. And the AAR rails, and this is RE, means it's an AREMA section, American Railway Engineering and Maintenance Away Association section, is in pounds per yard. Now, it just so happens.
You say pounds, but you write libras. What's the difference?
No, that's the standard symbol for pounds in the English language world. LB is a symbol for pound.
Okay, thank you.
And again, I'm being very careful to expose this to you, because again, for example, those of you who are working on metros, you're going to find references a lot of times to North American standards. When I was working on both Jerusalem and Tel Aviv, as a matter of fact, when I was working on Tel Aviv Metro, we actually used several U.S. standards, including their noise and vibration standards, as part of the design when we did the environmental noise statement for the Ministry of Environment in Israel for the Red Line. We use an American standard, and so you're going to be running across these things. So it's important to understand what you mean when you find it. Now, this is one of the places where the conversion becomes very easy. Basically, one kilogram, to convert from kilogram to meter to pounds per yard, you basically multiply by 2. You can go through, I probably have another slide that shows that later on, but very quickly, a 60 kilogram per meter rail is equivalent to 120 pounds per yard. A 54 kilogram per meter rail is equivalent to 108 pounds per yard. So 140 RE rail would be about 70 kilograms per meter. 132 RE rail would be 66 kilograms per meter. 100 RE rail would be 50 kilograms per meter. Okay. Now let me go back to the point I'm trying to make. Notice the overlay of the different sizes. So this is 50, 58, 66, and 70 kilograms per meter. Notice the heavier they are, the taller they are, the wider the base, the wider the web. Now, one of the things that we try to do with rail in all cases is to maintain the stability of the rail. So if I come back here, for example, let me just do it on this section. If I apply my vertical and lateral load here, and why am I applying it here? Because in a curve, this is where my wheel flange is. My wheel flange is exactly over here. So I have my lateral load here and my vertical load here. I want my base of my rail to be such that the vector resultant of the L and V as much as possible falls inside the base of the rail. Why? Because it's stable and will stand up by itself on the traffic. In 90% of the applications, you can actually remove fasteners and the rail will actually stay stable by itself because the vector resultant will not go outside of the base of the rail. The problem is in 10% it will, and that's where you need your fasteners. Fasteners also do other things like provide longitudinal restraint, which we've talked about before and we'll talk about again. But basically, we want to maintain this overturning stability. So what tends to happen is as the rail section gets taller, use a different color, it's hard to see here. As the rail section gets taller, the base gets wider. So you notice the 140 and 132 RE rails, so the 70 and 66 kilogram rails, tend to have a wider base, about 150 millimeters, as opposed to the smaller sections, which tend to have about 125 millimeter base. And again, you can see that over here. You can see the 150 millimeter base for the UIC 60, and for the shorter 54 and 49, you see the smaller base. And this is specifically designed to maintain this overturning ability, because as we get higher, we need to widen the base to make sure that I don't have a tendency to overturn.
Alan,
Yes,
what's the gain of higher rail?
stronger. As we'll talk about in a few moments, either the taller the rail, the greater the bending moment of inertia. That means for the same load, the stresses are less. So for example, under a heavy load environment, you can overstress. Let's go back to the your sections here. If I was in a mainline environment where I'm running lots of locomotives and heavy freight wagons, a 49 kilogram per meter section may generate excessively high stresses in my rail. Whereas if I go to a 60 kilogram section of rail with a moment of inertia that's significantly higher, then my stresses are correspondingly lower. So it's one of the ways to reduce the stresses in the rail. It also reduces the deflection. The deflection is lower for the heavier rail section.
But can't you do the higher points wider and get it short about the length. It will be short, but the width on the
It's,
top will be
okay.
higher.
So now we're going to get a little, now we're getting into sort of engineering mechanics design. Okay. Why? Do you know why we use an I-beam instead of a rectangular section in most construction? Because an I-beam is the most efficient design for giving you the maximum moment of inertia for the minimum amount of metal, and so for the minimum cost. And so by making the rail taller, it's much more efficient from a cost or from a amount of metal required point of view than trying to make the head much wider. And the reason is, again, if you remember your equations from engineering mechanics, the moment of inertia for a rectangle is BH cubed over 12. So the height has a cubic effect, whereas the base has a linear effect. So I get much more bang for my buck, so to speak, if I increase my height. If my goal is to increase my moment of inertia, to reduce my stresses, I get a much more efficient use of material by increasing my height. Did I answer your question?
Okay, thanks.
And by the way, you'll see this throughout. And you know, for example, in the UIC world, UIC 60 is about as heavy a rail section as you're going to get, which is equivalent to 120 pounds per yard. In the heavy axle load world, rail sections go up to as much as 141 pounds per yard. The heaviest rail section in the heavy axle load world is about 141 pounds per yard, which is 70 kilograms per meter. And that's because the higher loads. Now, I will say that for many, many, many years, the Russians actually had a heavier rail section. The Russians actually went up to about 75 kilograms per meter or higher. I think they've scaled back a little bit. And I think now they're equivalent to the AAR world with about 70 kilograms or 140 pounds per yard as being the highest sections they have. Here you can clearly see where these uses come in. In the heavy axle load world, a 60 kilogram per meter rail is considered to be a medium rail section. Again, if we go back over here, it's sort of in this range. It's just a little bit more than 115, it's 120. So it's considered to be a medium rail section. Whereas in the UIC world, it's really the heaviest rail section that you're going to see. And that's reflective of the differences in loading that I think we talked about in an earlier class. Again, just like we saw for the other UIC rail section, in addition to the major properties of the, let's go back to yellow so we don't clog everything up. We have the width of the rail, we have the height of the rail, we have the neutral axis, we have the transition radius. Actually in the AAR world, there's an even greater emphasis on transition on the radius at the top of the railhead, even though now that's starting to catch up in the UIC world. And we'll talk about the use of grinding to put a controlled radius into the railhead a little bit later. But again, we're going to come back and understand why this radius is so important in a few moments. This is a typical set of standards that's tabulated. You can see the moment of inertia, the weight, the areas of the head, web, base, and the whole section. So remember the A that we used for the thermal loads, EA alpha delta T. This is the area of the rail. Section modulus of the head is basically I over C. Lateral moment of inertia is the moment of inertia around the y-axis. Torsional rigidity of the rail. So there's all sorts of nice, useful information, a lot of which we're not going to get into in this class because we just don't have the time. But all this is pretty much standardized, tabulated in the standards and in the manufacturer's specs. So the good news is you don't have to go out and calculate moment of inertia. It's done for you. Now, there are a lot of subtle differences between rail sections. So for example, this is 136 RE rail is 68 kilogram rail. 132 RE rail is 66 kilogram rail. But you notice the designs are a bit different. In addition to the moment of inertia, look at the head. So for example, the radius on the top here is 14 inches versus 10 inches over here. This has a smaller radius. And what we've been learning and what we've been seeing is there's been a tend to going to a smaller radius. So 10 inches is what, 250 millimeters? So you got a 250 millimeter radius here as opposed to a 300 millimeter, no, 350 millimeter radius here. Notice the width is wider for the 132 versus 136. When these rails were originally designed, the 132 was actually designed for curves and 136 was designed for straight track. So the 136 had a deeper head and a somewhat slightly narrower width of the head because this was for straight track or tangent where most of the wear is on the top of the railhead. And the 132-hour rail was has a wider railhead and a not quite as deep depth of head. And this was more designed for a curve rail. So there was a lot of sophistication that also went into some of the section designs in there. And the newest rail section that I'm aware of that's been developed anywhere in the world is the 141 RE rail section, which is actually relatively new. It's only developed in the last 10, 15 years. And it was developed as a heavy rail section to give the longest life of the rail in service. Okay. So I should say, for example, that these are all called T-rails, because they basically look like an upside down T. Every once in a while, you'll see the name Vignoli rail. Has anybody ever heard the name Vignoli rail? I'm actually surprised because this, I know a lot of the European consultants use this term. Vignoli rail is another name for T-rail. So this kind of rail is considered to be T-rail or Vignoli rail. If you ever see the name Vignoli, that just refers to the fact this is a T-rail section. In addition to standard T-rail, we have grooved rail, which is also sometimes referred to as girder rail, where the rail has its own flangeway. So this is designed for the wheel flange to go in here. You'll see this in metro. So if you go to Jerusalem uses this through most of their embedded track. If you walk down the Rehov Yafo in Jerusalem, and you just look at the rail, you'll see girder rail throughout. Girder rail is not quite as strong as T-rail. In fact, the head of the rail can bend if it's not supported. So if you look, if you ever look at where girder rail is used, you'll always see that it's usually used in embedded track or primarily embedded track. That's where the most common uses are. Light rail or trolley rail, trolley systems, light rail systems, LRTs. And usually underneath this, if you look underneath the street, you'll see that there's usually some sort of filler material that goes in here that's used to actually help support the head of the rail. You can't actually take girder rail and leave it unsupported because the head would rotate on the web. The biggest advantage.
But this filling material, it's not strength enough to hold the rail. It's just like a gummy.
It's not strong enough to hold it. The design of this head is such that without this extra support, this head would rotate under traffic.
And do you think that the filler can support it? It cannot get any strength. It's very weak.
It's preventing it from rotating. It's not this. It's not being. It still has its vertical support of the steel. It still has its web here. This is just designed to prevent it from rotating. Yes. If you take a girder rail and just try apply, and you just apply leaving it in place without the support, after a time that rail will start to rotate. That head will start to rotate on the web. If you support it, it won't rotate.
I work a lot with grooved rail, but it's not support, as you say, against the twist, because it's all Edilon and insulation and all kind of material that are very weak.
It's weak, but it's dense. It provides. We're just looking at providing some overturning moment resistance. We're not supporting the load. We're supporting the overturning moment, which is different. Yes, the Allan systems use some sort of cork based. The Allan, I believe, is a cork fill, right? And
yes.
And some of the others use various types of plastics in here.
So we use cork-a-lot.
Okay, so use the cork. The cork is not it provides, but you fill up the entire area. You don't leave a gap, right?
Yes. Yeah.
Okay. So basically, you're trying to compress the cork. And that resistance is sufficient to prevent that from rotation, because we're not stopping it from compressing. I mean, we still have the web of the rail, so that's still supporting the rail. So the rail is not going to collapse vertically. The only thing you're going to do is you're going to make sure if you have a lateral load going around the curve to make sure it doesn't rotate. The primary reason for having girder rail as opposed to T-rail is to give you the flange weight for the wheel. There are some metros out there that use T-rail and then introduce a strap, which is bolted through the web of the rail, and they've introduced a flange way that way. This is more common in the heavier metro applications. But in the light rail transit, such as Jerusalem, which is a good example, they use the groove rail because it gives you a nice uniform flange way all the way around. I'm not in my office anymore. I actually have in my office. I actually have a piece of groove rail where the head's been distorted. So I can, unfortunately, maybe if I can get back to my office, if they let me into my office again one of these days, I can find it and bring it in. Any more questions about groove rail? Any more comments about groove rail? Okay,
Alan,
yes,
you said that a grooved rail will be common in light rails.
yes.
Is it appears also in heavy rails with concrete
Usually not.
platform? No.
Usually not. First of all, in a heavy rail environment, nobody likes to use groove rail because of its strength characteristics. And second of all, in most concrete slab applications, let me clear this, draw a picture. Okay, in most concrete slab applications, there's no problem leaving a gap for the wheel flange. The problem is an embedded track. An embedded track where you expect to have people walking, where you expect to have bicycles, where you expect to have some sort of pedestrian traffic. You don't want a gap at the edge of the rail. As a matter of fact, a number of years ago, I was involved in a lawsuit where they had actually put a piece of regular rail in an embedded track environment. There was a big gap. A bicycle rider came along. His wheel got caught in the flangeway. He fell over, got hurt, and sued the metro. You tend where you tend to use the groove rail is where there's a lot of pedestrian and other traffic on top up here. So you don't want to leave a gap. If you're using a concrete slab, such as a metro, underground metro, people don't walk down there. And walk down there also because you have a third rail as well. So you don't want to electrify them. So as a result, you can live with a bit of a gap. So almost all metros in the world, almost all heavy axle load metros use a standard T rail. It's only the light rail track that's primarily in an embedded track that uses groove rail.
Okay, thanks.
Okay, so rail tends to be stamped and branded with its manufacturing information. An example of so it's usually branded on one side and stamped on another. So branded, this is branding. Branding is where the letters are actually raised. And a fairly standard type of branding, it varies, but this is a fairly standard type of branding, would show the weight of the rail, the section, the manufacturer, the year it was rolled, and the month it was rolled. On the other side, it will be stamped. So that means the letters are instead of coming outward, they're inward, they're formed inward from stamping. And most rail that you're going to be exposed to is going to be continuously cast. So continuous cast rate would have the heat number, the type of rail, in this case, head hardened, the rail position, the bloom, and the method of hydrogen elimination. This would be a vacuum degassing type of approach, for example. We talked about the properties of the rail. You've seen this already before, but we haven't gone through all of them. So let's look at UIC 60 or UIC 54. We have the weight in kilograms per meter, or pounds per yard. We have the area. We have the moment of inertia. Now, again, just to give you an idea of the difference in a moment of inertia. So again, this would be the equivalent of a UIC 50 rail. This would be the equivalent of a UIC 66 rail. This would be a UIC 60 rail. Well, we have the moment of inertia here anyway. So you can see that a UIC 50 rail would have a moment of inertia of about 2,000 centimeters to the fourth. The UIC 60 rail would have a moment of inertia of 3,000. So for a 20% increase in weight, I get a 50% increase in moment of inertia. And if I was going to go up to a UIC 70 type of weight, I would be over 4,000. So I would be doubled. Lateral moment of inertia is tabulated. And we talked about this, we used this before, the neutral axis above the base and the height of the rail. Here, just to give you an idea of the differences between types of designs, I compare a UIC 60 with a 132 RE rail, which is really a 66, with an R65. This is a Russian rail section. So this is you're all familiar with UIC 60, a standard UIC design. This is a Riemann, a heavy axle load type of design, and this is a Russian design. So for example, you can see the bases are really the same. The heights of the rail are a little bit different, but that's because these two are a little bit heavier than this. But you notice the 66 and the 65 are both about 180 millimeters tall. UIC 60, which is 10% less weight, has about 172 millimeters tall. Width of the railhead, very comparable all the way across. Height of the railhead, neutral axis. You can see the designs are not all that dissimilar, but there's subtle differences between them. And quite honestly, there's a political issue involved here. The Russians have to have their own section, the Americans have to have their own section, and the Europeans have to have their own section. The reality of it is just about any mill in the world will make will certainly make these sections. The only Russian mills make Russian sections, but you can go to any mill in the world and order either a UIC or a RE section from an American mill, from a European mill, from a Chinese mill. They all have the rollers to make either UIC or RE sections. So let's take a break right here before I go into rail overturning. Let's take a 15-minute break and we'll continue from here. We'll continue. So I've got, I'm on the half hour. So let's 1:45, let's reconvene.